In this video, we're going to introduce numerical integration. Why do we need numerical integration? The goal is to evaluate the definite integral a to b f of x dx by applying the fundamental theorem of calculus. We need to find an antiderivative capital F of x of f of x. And sometimes this is an impossible task. Here are some examples. For example, integral from 0 to 1 e to the x squared dx. We don't know an antiderivative for e to the x squared. No such antiderivative exists. Similarly, integral from 1 to 2 cosine of x squared dx. We can't integrate this using the fundamental theorem of calculus. So we have to apply a numerical technique, such as trapezoidal rule, Simpson's rule, or midpoint rule, and we're going to be looking at all of these rules. Another example is the integral from 2 to 3 1 over 1 plus log x dx. Case 2, the other case is it results from functional values, such as velocity, for example, recorded at equally spaced intervals. So here's an example. Here we have velocity measurements of a runner given at different points in time. And our goal is to estimate the distance traveled. So basically, our goal is to estimate the integral from 0 to 8 v of t dt. In both of these cases, we need to find approximate values of the definite integral of the form integral a to b f of x dx. So let's review the Riemann sum that we have covered before, such as left-hand rule, right-hand rule, and midpoint Riemann sums. All right, so for the left-hand rule, we have integral a to b f of x dx. That's equal to I goes from 1 to n, f of xi minus 1, evaluate the function at the left endpoints of every interval, times delta x. The right-hand rule, we evaluate the function at the right-hand points of every interval. Summation, I goes from 1 to n, f of xi, delta x. And the midpoint rule, we evaluate the function at the midpoint of every interval. Summation, I goes from 1 to n, f of xi bar times delta x, where xi bar is the average of the left-hand and right-hand values of x. So in general, delta x is equal to b minus a over n. That means we have equal partitions. Xi is a plus I delta x. Those are the values of x that are equally spaced. And I ranges from 1 to n. All right, so you can see that here we have a graph, and the left-hand rule is given by the green shaded area, and the right-hand rule is given by the gray shaded area. You can see how the left-hand rule is going to, which is the green part, the green shaded area, is going to underestimate the actual area of the curve. And the right-hand rule is going to overestimate the area under the curve. And the reason, of course, is because the function is increasing in this case. All right, so let's now derive the trapezoidal rule. We define the trapezoidal rule as the average of the left-hand and right-hand point. So what we have is integral from a to b, the definite integral, f of x dx. We're going to estimate that with trapezoidal rule. And we're defining the trapezoidal rule as the average of the left-hand and right-hand rules. So here we have I goes from 1 to n, f of xi minus 1, delta x, plus I goes from 1 to n, f of xi, delta x. And I'm going to factor out the delta x, so we get delta x over 2 times summation, I goes from 1 to n, f of xi minus 1 plus f of xi. All right, there it is, and let's bracket this all inside the summation. So now what we have is delta x over 2. Let's expand this summation. If we plug I equals 1, we get f of x0 plus f of x1. That will give us the first term, basically. Well, it's actually two terms, but it's a first pair. Plus, now put I equals 2, and we get f of x1 plus f of x2. And now let's put I equals n, and we get f of xn minus 1 plus f of xn. Now, you will notice that these terms add up twice. We get 2f of x1, 2f of x2, and so on. So let's rewrite that. That's going to be Tn, trapezoidal approximation with n intervals, is delta x over 2, divide by 2 because we're averaging the left-hand and right-hand rule. And we get f of x0 plus 2f of x1 plus 2f of x2 plus all the way to 2f of xn minus 1 plus f of xn. Notice the pattern 1, 2, 2, 2, all the way to 1. So the first and last are just ones, and all the middle terms have 2's in front of them. Delta x is equal to b minus a over n. Xi is a plus I delta x, and I ranges from 0 all the way to n. All right, let's illustrate this with a diagram. So here we have a trapezoid. You can see how we have the function is being evaluated at the left endpoint, and the function is evaluated at the right endpoint. And when we average them, we get a trapezoid. This is the top base of the trapezoid. And the area of this trapezoid is average height times the width. So it's going to be delta x over 2 times f of xi minus 1 plus f of xi. If we add up all of these trapezoids, we obtain the general trapezoidal rule formula. So let's write that down. Tn is equal to delta x over 2 times f of x0 plus 2f of x1 plus 2f of x2 plus 2f of xn minus 1 plus f of xn, and delta x, that's the partition width, is b minus a over n, equally spaced intervals. Xi is a plus I delta x. I ranges from 0, 1, 2, all the way to n. This is a formula for trapezoidal rule. You can think of it as a 22 rule because all the middle terms have 2's in front of them. The first and last, of course, just have 1's. So it's 1, 2, 2, 2, 2, all the way to 1. All right. So we're going to look at some examples. Here we have applied a trapezoidal rule and a midpoint rule with n equals 5 to approximate the integral from 0 to 1 x squared dx. So what we're given is n equals 5. The lower limit is a equals 0. The upper limit, b equals 1. Delta x is b minus a over n. That's 1 minus 0 over n. 1 minus 0 over 5, because n is 5 partitions. That's equal to 0.2. That's our delta x. So we draw a line here, and that's all we need. Basically, we know we're going to put 2 in front of all of these, 2 times the functional value, evaluate these x values, and 1 here and a 1 here. So very easy to do. Integral from 0 to 1 x squared dx is approximated by the trapezoidal rule, T5. That's delta x, which is 0.2, divided by 2, times the function evaluated at 0, plus 2 times the function evaluated at the x value of 0.2, plus 2 times f of 0.4, plus 2 times f of 0.6, plus 2 times f of 0.8, plus f of 1. Now the function is f of x is equal to x squared. So let's evaluate this. T5 is equal to 0.2 divided by 2, that's just 0.1. What is f of 0? Plug into the formula, f of x equals x squared, because that's our function. F of x equals x squared. So we get 0 squared plus 2 times 0.2 squared plus 2 times 0.4 squared plus 2 times 0.6 squared plus 2 times 0.8 squared plus 1 squared. If we put this into a calculator, we get T5 is 0.34. That's a trapezoidal rule approximation to this definite integral. All right, now let's look at the midpoint rule. So we have the same n. We have n equals 5, a is 0, b is 1, delta x is b minus a over n. That's the same, 1 over 5. That's 0.2. The function is f of x is x squared. And m5, midpoint rule approximation. We're going to approximate the definite integral with the midpoint rule, 0 to 1, x squared dx. With the midpoint rule, we have to evaluate the function at the midpoints of every interval. At point 1, point 1 is the average of 0 and point 2. At point 3, at point 5, at point 7, and at point 9. So the integral from 0 to 1, x squared dx, is being approximated by the midpoint rule with 5 partitions. That's m5 is equal to delta x times f of point 1 plus f of point 3 plus f of point 5 plus f of point 7 plus f of point 9. Now the function is f of x is equal to x squared, so let's plug it into the function. M5, midpoint rule approximation, 5 intervals. 0.2, that's delta x. F of 0.1 is 0.1 squared, because f of x is x squared. F of 0.3 will be 0.3 squared. And f of 0.5 is going to be 0.5 squared. Plus f of 0.7 is 0.7 squared. F of x is x squared. F of 0.9 lastly will be 0.9 squared. If we put this into a calculator, we get m5 is 0.33. All right, now we chose the definite integral 0 to 1 f of x dx, 0 to 1 x squared dx, so that we can examine how accurate these estimates, trapezoidal rule with 5 partitions and midpoint rule with 5 partitions, are as compared to the exact value of the integral. And the exact value can easily be computed using the fundamental theorem of calculus. So let's do that. Integral from 0 to 1 x squared dx is equal to x cubed divided by 3, reversing the power rule, apply the fundamental theorem of calculus from 0 to 1, and we get 1/3. So what we have from before, T5 is 0.34, trapezoidal rule approximation. M5, we found it to be 0.33. And the exact area under the curve is 1/3, where we applied the fundamental theorem of calculus. Now let's compare the errors. So the error trapezoidal is the integral from 0 to 1 x squared dx minus the trapezoidal approximation. That's going to be 1/3 minus 0.34. Plug into a calculator and we'll get minus 0.0066 repeating. And the error of the midpoint rule, that's going to be the integral from 0 to 1 x squared dx minus the midpoint approximation. That gives us 1/3 minus 0.33. That's equal to 0.0033. Notice how the error of the midpoint rule in terms of magnitude is half the error of the trapezoidal rule. And also notice that they're opposite in signs. In later videos, we will talk about that. We will talk about why the midpoint rule and trapezoidal rule give us errors that are opposite in sign. All right, thank you.